Welcome to Essential Problems of AP Chemistry. This problem is associated with finding the light absorbed or released in the electronic transition within a monoelectric atom. That is, an atom that only has one electron. The situation gets much more complicated when we have more than one electron and is beyond the scope of this course. The tools that we'll need will be the following equations. C is equal to lambda nu, which relates the speed of light to both light's wavelength and frequency, as well as the energy, Planck's equation, that light in its quantization can hold, the relationship between its frequency and energy. E is equal to h nu. We have already combined these equations into one form, which we can also use, which is E is equal to hc divided by lambda. We also have the equation associated with the Bohr model. Change in energy for the electronic transition is equivalent to negative 2.178 times 10 to the negative 18th joules times z squared over nf squared minus z squared over n initial squared. In this example, we're going to take an electron in a 1s sublevel of a nickel 27 plus ion and calculate the wavelength of light that must be absorbed in order for that electron to be completely ionized, that is, to be no longer attracted to the ionic nucleus. To solve, we first need to organize our information. Z is the number of protons, and make sure that you have this correct. It is not 27. 27 plus is the ionic charge. Looking on the periodic table, nickel has 28 protons. Therefore, Z must be 28. N initial refers to our initial energy level. The 1s sublevel is in the first energy level. Therefore, N initial is 1. And N final, the final energy level, well, that's infinite, infinitely far away. So here we have undefined. Substituting in, change in E is equal to negative 2.178 times 10 to the negative 18 joule times 28 squared divided by undefined squared minus 28 squared divided by 1 squared. Simplifying this due to what we have already discussed in class, that the limit as any number divided by undefined approaches infinity is equal to 0. We can simplify this to negative 2.178 times 10 to the negative 18 joules times negative 28 squared divided by 1 squared, which gives us a positive value of 1.707 times 10 to the negative 15th joules. This is the energy that must be absorbed for the electron to go from the 1s sublevel from there to be completely ionized. Note that this is simply the kinetic energy that must be absorbed. In our example, though, we are using light. Therefore, in order to convert this to light, we take that exact amount of energy and substitute it into our light equation, relating energy to wavelength. Rearranging that equation, wavelength is equal to hc over E, and substituting in with Planck's constant and the speed of light, dividing by that energy that must be absorbed, we get a value of 11.63 times 10 to the negative 11th. In solving this, you should definitely put into your calculator just 6.626 times 2.9979 divided by 1.707552 and simplify the scientific notation right after that. That will eliminate the possibility for errors using your calculator. Finally, we can simplify, and many times it's reported in nanometers. we have 0.1163 nanometers, according to the correct number of significant figures, and that is light that must be absorbed. In addition to solving the problem both forwards and backwards, that is, from using a wavelength to find an unknown energy level, or from using energy levels with associated transition to find wavelength, there are also a number of key ideas that you should be comfortable with. First, if change in energy is positive, then kinetic energy is being absorbed. And if change in energy is negative, then kinetic energy is released. Recall that the equation below was derived from comparing two different states. And that constant, negative 2.178 times 10 to the negative 18 joules, was derived from the potential energy that an electron has in the hydrogen atom. It is the energy value of that ground state electron. And of course, since that electron is bound, attracted to the nucleus, it is a negative value. In finding the difference, you are finding the kinetic energy that must be absorbed or released for that transition to occur. Of course, that attraction that electron has to the nucleus is based upon, it's proportional to, the quantity of charge. Hence why you are multiplying that factor times z squared. You are also dividing that factor by the distance, effectively, between the electron and the nucleus. Therefore, it coincides with what we have already discussed, which is the attraction is inversely proportional to the distance between the charge. Signing out, Crit.